So far in the fluids unit, we've only talked about what happens if fluids are stationary. So we haven't dealt with fluids that are moving. And tonight we're going to do that. The first thing we want to talk about is continuity. Now continuity is kind of like Pascal's principle, except for a moving fluid. The principle of continuity says that if a fluid is incompressible, now incompressible means that the density of the fluid does not change. So rho is constant. The idea here is that there are some fluids, most gases in fact, that you can squeeze them together and take their same mass and put it in a smaller volume, and you can change their density. But with something like water, it's really hard to squish water together, so water generally keeps its same volume as far as how much mass is there. So mass over volume stays the same for water, very hard to change it. But for a gas, you can easily squeeze a gas into a very small container, thus increasing its density. So if a fluid can't be squeezed, a smaller cross-sectional area, so these kind of things right here, these are the cross-sectional area, meaning if I just split a pipe through, that's the cross-sectional area, will cause the fluid to flow faster. So in this diagram at the top, when the fluid is in this larger area, so it has a large cross-sectional area, the velocity vector is smaller. So notice it here, the velocity vector is smaller. But when the fluid moves into this smaller cross-sectional area, the velocity vector increases because the fluid went faster. So the smaller the pipe you shove the fluid through, the faster it will go. And if you've ever played with a garden hose, you've probably experienced this. If you want to spray somebody with a garden hose, you probably don't just aim the garden hose at them. You put your finger over part of the top of the garden hose, thus decreasing the area the fluid flows through, and you'll find that if you put your thumb over the end of that garden hose, the water comes out much faster. It'll go further, and you can really squirt somebody. And so, whenever you've done that, if you've gotten to play with a garden hose and kind of put your thumb over the end, you decrease the cross-sectional area, you made it smaller, and the fluid had to speed up. This is because whatever mass I shove into this smaller area here has to come out the other side. And if I get a smaller area and I'm shoving more and more mass in, the mass that was there before has to get out really quickly to make room for the mass that I'm shoving in behind it. So really it's about conservation of mass, that whatever goes in has to come out. And so the smaller we make that area it travels through, the faster the mass in front has to get out of the way so more mass can come in. And that's the principle of continuity. That if you take a fluid that's flowing through a big cross-sectional area, squeeze it down to a small cross-sectional area, it will speed up. Alright, continuity can be expressed mathematically as area 1 times velocity 1. Notice these are not volumes. Volume is usually a capital V, and velocity is usually a lowercase v. So that's the difference. Area 1 times velocity 1 equals area 2 times velocity 2. The area is the cross-sectional area measured in meters squared. And if you're confused about cross-sectional area, imagine a cylinder that we cut open down the middle. If we were to find the area of that circle that's at the end of the cylinder, that's the cross-sectional area. V is the velocity of the fluid, and then the term AV together is called the volume flow rate. That comes out of that area is in units of area, meters squared, and velocity is meters per second. If we multiply those, we get meters cubed over seconds, which is basically a volume per time, and we call that the volume flow rate. Water flows at a speed of 1.4 meters per second through a pipe that has a cross-sectional area of 25 centimeters squared. If the pipe narrows to 15 centimeters squared, 1. What is the speed? At what speed will the water flow? 2. What is the volume flow rate in the wide section? Remember, volume flow rate is just area times velocity. What is the volume flow rate in the narrow section? Okay, let's make this happen. So first, I'm going to take these cross-sectional areas, and convert them to meters squared. This is not as easy a task as you might expect. We're going to have to go back to dimensional analysis, which we did at the very beginning of the year. we cannot simply move the decimal 2 places because there are not 100 centimeters squared in a square meter. There are actually 10,000 centimeters squared in a square meter. So we're going to need to do that conversion using dimensional analysis. Okay, so I want to convert 25 centimeters squared into meters squared. So I need to multiply this by something that has centimeters squared on the bottom, meters squared on the top. Well, maybe I can simplify this a little bit. I know that for every 1 meter, there are 100 centimeters. And I noticed that both of the units got squared, so that must mean that the numbers got squared too. So that would still be 1 meters squared over 100 squared is 10,000 centimeters squared. So now I need to divide 25 centimeters squared by 10,000, and that will convert it to meters squared because the centimeters will cancel out. 10,000's on the bottom. We're just multiplying the top by 1, and I'll end up with meters squared. So let me do that real fast. Dividing by 10,000 is just going to move the decimal 4 places to the left. 1, 2, 3, 4. So that means my cross-sectional area of that first one, A1, is 0.0025 meters squared. And I can use that same principle of moving the decimal 4 times to the left for 15. 1, 2, 3, 4. Second area is 0.0015 meters squared. Now we're ready to go. At what speed will the water flow? Okay, so the principle of continuity tells me area 1 times velocity 1 equals area 2 times velocity 2. And that first area is 0.0025 meters squared with a velocity of 1.4 meters per second. Now you might wonder, Mr. Melvin, why didn't you solve that equation before plugging in the numbers? Because I noticed these last 2 questions ask me to find AV. So if I go ahead and set the equation up so when I multiply this left side, I will have answered this question. So why not go ahead and plug in the numbers since I'm going to have to later anyway. Equals the second area, 0.0015 meters squared, times the velocity we want to know. So the velocity when it gets here. The problem tells us that when it's over here on this left side, it's 1.4 meters per second. We want to know what it is when it gets over here. So that's going to be V2. Well, that's simple. I multiply the left side, divide by 0.0015 to get rid of this, and I'll have V2. So if I solve that for V2, I get that V2 equals 2.33 meters per second. Now we learned that smaller cross-sectional area will make the fluid flow faster, and this does. According to this, the fluid sped up, went up to 2.33, and so our answer makes sense. I'm going to say that seems right to me. Next question, what's the volume flow rate in the wide section? Well, I've already done that. Look, it's right here. 0.0025 times 1.4 meters per second, because AV is volume flow rate, so 0.0025 times 1.4 is 0.0035. So that means the first volume flow rate is 0.0035 meters cubed per second. And so that's just doing area 1 times velocity 1, these two numbers here. All right. Now I want to know the volume flow rate in the second section. Okay. Well, that would be A2 V2. We already know A2 is 0.0015 meters squared, and we just found V2. So let's do that. A2 V2 equals 0.0015 meters squared times 2.33 meters per second, and I get 0.0015 times 2.33, 0.0035 meters cubed per second. Sorry, that slide got a little sloppy. But the point here is I got the same thing for both, which is what the principle of continuity tells me. It says A1V1 equals A2V2. So they should both be the same. And that's it. Sorry this slide got a little sloppy. Hopefully this idea is simple enough that it didn't throw you off too bad.